In the last section of 2.1, we're going to look at the properties of limits. And there are a number of properties of limits we'll use throughout the course. I'll try to make these a little bit bigger. First of all, it says that let f and g be defined for all values where x doesn't equal a over some interval in the interval containing a. Assume that L and M are real numbers, such as the limit as x approaches a of f of x is L, and the limit as x approaches a of g of x is M. Let C be a constant, and each of the following statement holds true. If I have the limit as x approaches a of one function plus another function, that is equal to the limit as x approaches a of the first function plus the limit as x approaches a for the second function. Similarly, the same rule applies for the difference of two functions, as you can see here. Our constant multiple law for limit says if I have a limit as x approaches a of a constant times a function, then we can move that constant out front and take the limit as x approaches a of the function and then times it by the function. The product law says the same thing. If I have a limit of two functions being multiplied, I can take the limit of each individual function and multiply their results together. Similar for the quotient law, provided the limit of the denominator doesn't equal 0. The power law for limit says if I have the limit as x approaches a of some function raised to a power, I can do the limit of the function first and then take the power of the whole thing. Similarly, for the root law of a limit, if I have the nth root, the limit of the nth root of a function, I can take the limit of the function and then apply the root to that entire limit. Okay, let's see how these apply in some examples. Let's say, for example, we are given the following. The limit as x approaches a of f of x is -3, the limit as x approaches a of g of x is 0, and the limit as x approaches a of h of x is 8. Find the limits if they exist. So in part A, we're looking for the limit as x approaches a of the sum of two functions. I'm just going to do the solution down here. So this is really going to be equal to the limit as x approaches a of h of x plus the limit as x approaches a of f of x. And I can break this up now because the limit as x approaches a of h of x is given to me as 8. The limit as x approaches a of f of x is given to me as -3. So 8 plus -3 is going to be -5. Okay, so let's take a look at the next one. So if I look at our next example, question B, we have the limit as x approaches a of a function all squared. So this is really equal to the limit as x approaches a of f of x all squared, which is going to be the limit as x approaches a is -3 all squared. So this limit is going to be 9. Again, pretty straightforward. Let's take a look at question C. So in question C, we have the limit as x approaches a of 2 times f of x divided by h of x minus f of x. So this is really going to equal the limit as x approaches a of 2 times f of x divided by the limit as x approaches a of h of x minus the limit as x approaches a of f of x. Now using our constant rule, I'm going to bring the 2 out front. So this is really 2 times the limit as x approaches a of f of x. And in the bottom, we've already applied the difference rule, so I can substitute in place of h of x. I'm putting in 8. F of x, it's going to be minusing -3. So this is going to be 2 times the limit as x approaches a of f of x, which is -3, all over 8 minus -3. And this works out to be -6 over +11. So there's using our limit properties and some of the examples you could see moving forward. Okay, let's take a look at these limit properties when we're reading these values off of graphs. So let's start with, I'll just make this a little bit bigger here. Okay, so we have the limit as x approaches 0 of f of x and the limit of as x approaches 0 of h of x. So we're going to use our limit property and say this is really the limit as x approaches 0 of, that's not very neat, let me just rewrite that. This is going to be the limit as x approaches 0 of f of x times the limit as x approaches 0 of h of x. And again, these I'm going to read off of the graph, so be careful that you have the correct graph. There's f, h, and g. So the limit as x approaches 0 of f of x is negative 1 times the limit as x approaches 0 of h of x is positive 1. So this limit is going to be negative 1. Looking at b, this is the second one here. This is going to be the limit, or equal to the limit as x approaches 0 of h of x divided by the limit as x approaches 0 of g of x. The limit as x approaches 0 of h of x is 1. And the limit as x approaches 0 of g of x is 0. And therefore, this does not exist because the 1 divided by 0 is undefined. Okay, let's take a look at the next one here. So I have the limit as x approaches negative 2 of f of x plus g of x. Now, this is going to, when you take a look at this, first of all, some of you might think, okay, that negative 2, the limit from the left and the right aren't the same, so the limit of the sum can exist, but you have to be careful with this. You have to check both sides. So let's do the limit as x approaches negative 2 from the left of f of x plus the limit as x approaches negative 2 from the from the negative side of g of x. So we're breaking up using our sum rule. Well, coming from the left of negative 2 on f, that is going to be equal to 1 plus coming from the left of negative 2 on graph g, which is the one down here, it is going to be 3, and 1 plus 3 is equal to 4. Now, if we do the same thing, if I find the limit as x approaches negative 2 from the positive side of f of x, and I add to it the limit as x approaches, actually, you know what, I'm just going to work this out down here where there's a little bit more room. So now we're going to do the limit, this is still part A, the limit as x approaches negative 2 from the positive side of f of x plus the limit as x approaches negative 2 from the positive side of g of x. Well, coming from the positive side of negative 2, this is 3. Coming from the positive side of negative 2 of g is 1. This also equals 4, so this limit is equal to 4. So even though the individual limit at negative 2 doesn't exist, if you check the left and right hand side for part A, the answer does work out to be 4. Okay, let's make some space here for the second one. Again, if you want to see the full solution again, just stop and rewind the video. For part B, we have the limit as x approaches 1 of f of x plus the limit as x approaches 1 of g of x. And again, at 1, it's undefined, and S, you have to do both sides. So we're going to do the limit as x approaches 1 from the negative side of f of x plus the limit as x approaches 1 from the positive side of g of x. And if I work that out, coming from the left of 1 for f is going to be 2. And coming from the negative side of 1, it's going to be 0. So this limit is 2 coming from the negative side. And now let's do the limit as x approaches 1 from the positive side of f of x plus the limit as x approaches 1 from the positive side of g of x. So this is going to be negative 1 plus 0. G equals negative 1. So therefore, the limit for this does not exist because the limit from the left does not equal the limit from the right. Again, I'm going to get rid of this. You can rewind the video again to watch this one. And finally, I'm going to give you a second to try this one here on your own. So just pause the video and try question C. Well, I'm hoping you get a chance to try this one. And again, this is going to be, again, the limit as x approaches 1. I have a break there at 1, so I have to do left and right. So the limit as x approaches 1 from the left of f of x, applying my rule for the product of limits, this would be the limit as x approaches 1 from the left of g of x. So coming from the left of 1, this is 2 times, coming from the left of 1 and function g is 0. So this product is 0. And then let's do the limit as x approaches 1 from the positive side of f of x times the limit as x approaches 1 from the positive side of g of x. Coming from the positive side of 1 is going to be negative 1. Again, the positive side of g coming from the 1 is also 0, so this is going to be 0. So therefore, the limit of my question is going to be 0, because coming from the left and the right, they're both 0. Okay, let's take a look at the limits of composite functions. Okay, and again, when we do composite functions, again, this is really going to equal g of the limit as x approaches 3 of h of x, which is going to be g of, well, let's take a look at the limit as x approaches 3 of h of x, and as x approaches 3, the limit is 2. So then I am looking for the value of g of 2, and g of 2, if I read it off this graph, is going to equal 0. All right, the limit as x approaches negative 1 of h of g of x. Okay, again, using our composite rule for limits, this is going to be the limit as x approaches negative 1 of g of x. And I'm going to take that answer and plug it into h of x. So if I look at the limit as x approaches negative 1 of g of x, this guy does not exist. So since this part doesn't exist, neither can h of this part, so the answer to this limit does not exist. Okay, let's take a look at the next one. We have the limit as x approaches negative 3 of h of f of x. So again, using our composite rule, this is going to be the limit as x approaches negative 3 of f of x. So the limit as x approaches negative 3 of h of x. At negative 3, the limit is approaching 1, and h of negative 1 is, we take a, the limit as x approach of f of x, is the bottom one, is 1, and then h of 1, if I go to my h graph, it's undefined, so again, this limit does not exist. Okay, so there is our assignment for the last part of section 2.1, using our properties of limits. So you have your assignment from your textbook, that's the AP Calc textbook, and there's also a handout that I have for you for the limits of combined and composite functions, and the handout is right here. Okay, so you can give that a whirl. And if you have any questions, feel free to ask.